So we've got these two waves added together, the one with frequency 0.1 hertz, one with frequency 0.11 hertz. And it takes 50 seconds to go from loud to quiet, and then another 50 seconds to go from quiet to loud. So that time span from loud to quiet would be the beat period. So we would say that this amount of time from loud to the next loud, that would be the beat period. And then the inverse of that, I guess in this case, this would be 100 seconds. The inverse of that would be the beat frequency. And that would be 1/100th of a second, or 0.01 second, or hertz, sorry, 0.01 hertz. Because that's the inverse of the beat period. So that's just the amount of time from loud to loud. And note that that's exactly the difference between the two frequencies. In this situation, F1 is 0.1 hertz, F2 is 0.11 hertz. The beat frequency is the difference between them. Usually written in absolute value, just so it doesn't matter which order we subtract. So the beat frequency, how many loud to loud cycles happen per second, is the difference between the two frequencies. The difference between the two frequencies tells you how often there's a beat. And 1/100th of a hertz just means there's a 100th of a cycle every second. Or to put it another way, it takes 100 seconds for one cycle to happen. Any questions on that so far?
So then if we wanted to measure the beat frequency, just looking at a beats graph, we would probably kind of take the highest crest of one beat and the highest crest of the other beat and record the distance.
Yeah,
right?
You're looking for the large amplitude zone and the next large amplitude zone. And that can kind of be difficult to see just by looking at it, because it's not always going to be exactly on a crest or a trough. Like in this case, the actual point where it's the highest interference is actually going to be at 0, which is at equilibrium. So I think actually here the beat period would be from 0 to 100. That would be the constructive interference to the next constructive interference. So from 0 seconds to 100 seconds. Or you could say from quiet to quiet, from 50 to 150 would be the next one. It's also sometimes helpful to draw in what's called the wave envelope, which is basically just a curve sketched that encloses all of this. So something like, and this isn't exactly it, but something kind of like that. So that's a rough sketch of the wave envelope. It's basically just describing how the amplitude changes. Like here you've got strong amplitude, then the amplitude gets smaller and smaller, and then at this instant, at 50, the amplitude is 0. And then the amplitude starts to get bigger again. So the wave envelope is a useful way of visualizing this idea of beats also. We're going from large amplitude to 0 amplitude to large amplitude again. The amount of time it takes from large amplitude to large amplitude, or from 0 amplitude to 0 amplitude, is the beat period. And the inverse of that, the beat frequency, is literally just the difference between the two frequencies of the different sources. As opposed to the carrier frequency is just the actual frequency of the sound you hear. Like in this case, if you measure from crest to crest on this wave, or from trough to trough, that amount of time is the carrier period. The carrier period is the period of the actual wave. So the amount of time from crest to crest or from trough to trough of the actual wave itself. And the carrier frequency is just going to be the inverse of that. Which will also be the average of F1 and F2. So in this case, you take the average of 0.1 and 0.11, you get 0.105. So the frequency of these oscillations is going to be 0.15. Or sorry, 0.105. Any questions on that so far? And the carrier frequency basically just tells you the note you actually hear. Like if you're listening to two sounds with different frequencies, but they're pretty close, your brain interprets that as just one note with the average frequency of the two frequencies as the note you hear. But the beat frequency tells you how many times per second that seems to be wobbling from loud to quiet to loud. Also, if we change the frequencies a little bit, let's say we change this to, instead of being offset by 0.01, let's say we have it offset by 0.05. Note that we're now getting beats more frequently. We're going from loud to quiet to loud to quiet to loud to quiet in a much shorter amount of time, because we have a larger difference in frequency, the difference between 0.1 and 0.15. A larger difference means a higher frequency of beats. The beats are coming in more rapidly. Whereas if I make them further apart, let's say 0.1 and 0.105, it takes even more time for a beat to happen. So the closer the frequencies are, the further apart the beats are, the lower the beat frequency is. Whereas the more out of tune they are, like if I make these really out of tune, 0.1 and 0.2, the beats happen very quickly. You go from loud to quiet to loud to quiet to loud to quiet in a much shorter amount of time. Any other questions on that so far? Or any other questions on beats in general?
So I guess if we can look at this beat graph, we can determine what the carrier frequency and the beat frequency is,
Yeah.
and then we can kind of decide what F1 and F2 are.
Right, because we know that if you know the two values, the carrier frequency and the beat frequency, carrier frequency tells you the average. So you want values equal distance on each side of the carrier frequency. Whereas if you know the beat frequency, that tells you what the difference has to be. For example, let's say we know those values. A different example, not the one actually shown in the graph here, but let's say we know that the carrier frequency is 500 hertz. And we know that the beat frequency is, let's say, 6 hertz. And we want to know what are F1 and F2. So what do we know about the two frequencies if all we have is the carrier frequency and the beat frequency?
Well, we know F1 minus F2 is 6. F1 plus F2 divided by 2 is 500.
Yeah, so we could set this up as equations. The difference has to be 6, and the order doesn't matter. We can just say, assume F1 is the larger one and F2 is the smaller one. And we also know that their average is 500. So you could treat this as a system of equations and solve it that way. For instance, multiply both sides by 2, and you get F1 plus F2 equals 1000 hertz. And then just add these equations together. You get F1 plus F1 is 2F1. F2 plus negative F2 is 0. 6 plus 1000 is 1006.
Wait, could you go over the math again from the top?
Yeah, so from these equations, we know that the difference has to be 6 hertz. So we can write that as subtraction because that's the beat frequency. And we also know that the average has to be the carrier frequency, 500 hertz. One way of solving a system of equations like this is to, since these are both in what we call standard form, we just got something F1 plus something F2 equals something. All the variables are on one side and in the same order. One way we can solve that is by using multipliers to make these to make one of the variables have equal and opposite coefficients. Like we've got a negative 1 F2 here, we've got a 1/2 F2 here. If we multiply both sides by 2, we get the 2's cancel out, so we get F1 plus F2 equals 1000 hertz. And now if we just add these equations together, if we take the F1 minus F2, so we add the left sides together and add the right sides together, So we're basically just adding 6 hertz to both sides. It's just that on the right side, we write it as 6 hertz. And on the left side, we write it as F1 minus F2 because F1 minus F2 is 6 hertz. So we end up with F1 plus F1 is 2F1. F2 plus negative F2 is 0, so those cancel out. 1000 plus 6 is 1006 hertz. And then you can just divide both sides by 2 and get F1 equals 503 hertz. Then you can plug that back into the other equation. 503 minus something is 6, and solve for F2. So that's one way to do it. You can set it up as a system of equations. Any questions on the math there so far? Also, an alternative way to do it that might feel more visually obvious is if we set up a number line and put a mark at 500. And we want to make sure we have 2 values that are equidistant from that. We want a value that's some distance, some amount larger, and another value that's the same amount smaller, because we want these 2 values to average out to 500. But also, how far apart do we want those values to be? Yeah, we want the distance between these to be exactly 6. So if you have 2 values that are 6 apart and equidistant from 500, how far in each direction are you going? Right, so we can just say 500 plus 3 on one side and 500 minus 3 on the other side. So that's another way to do it. Set it up on a number line, put the carrier frequency as the average, and imagine you're going the same distance in both directions to get to F1 and F2. Take into account how far apart those are supposed to be. That's the beat frequency. And so you can just go halfway in either direction. So that's another way to get this, more visually rather than algebraically, but they both should lead to the same result, just different ways of doing the same thing. Any other questions on that so far? All right, then let's take a look at the double slit experiment, which is another example of interference, but in a very different sort of way. What sort of situation has to be happening to cause the double slit effect in the first place?
You need a wave.
Yeah, you got to have a wave, and what does that wave have to encounter?
2 slits.
Right, so let's say we start with a wall that has 2 narrow slits in it. And the terminology we're going to use here, we're going to say the distance between those slits is D. So that's limitation on the slit size. The slits need to be small and close together. And I think that that's specifically small in comparison to the wavelength of the light and close together in comparison to all the other distances. Because what we're going to do here, we're going to assume we have another wall some distance out here. Make that narrower. So assume we've got some white wall or projector screen or a sheet of paper or whatever over here that the light can actually hit. The important thing to assume is that the distance to the other wall, the distance the light is traveling, is very large compared to the distance between slits being very small. And the usual notation we use for that, we're going to call the distance between slits lowercase d. So that's the distance between slits. And then capital D, or sometimes capital L, depending on the textbook, is the distance from wall to wall. So that's the usual notation used. And the important thing is that the distance between slits be very small compared to the other distances involved. If that's not, and this is largely just because in the calculations, we're going to be making some slight approximations that are perfectly valid as long as this distance is small compared to this distance. If this distance is not as small or this distance is not as large, then the approximations kind of fall apart. But let's assume this is a small distance. So that we're kind of exaggerating this. This really should be, if we made this to scale, this should be more like something like this. But that makes it difficult to see what's going on. So we're exaggerating this distance so that we can see what's going on more closely. So let's say we have some light shining on this wall with slits in it. So we've got a light source somewhere back here. And that might be a light bulb or a laser, or it might even just be sunlight, but you've got some light expanding outwards from there. And if you draw out the ray tracings, or not the ray tracing, let's say you draw out the wavefronts first. If you draw out wavefronts spreading out from this source, so these represent crests and then troughs in between. Those crests, those wavefronts hit the wall and stop, or maybe bounce back. We don't really care which one, except what's the only place where they actually get through?
The slits.
Yeah, the slits themselves. And because it's coming out through these slits, which is basically single points, we can treat the slits as if it's a new source for the wave. So we can treat the wave as spreading out as a circular wavefront coming from that slit, as if it's the new source. And so we've got waves emanating from that slit, and we've also got waves emanating from this slit. And at every location, we can check for interference. Because, for instance, if we look at, let's say, this location here, looks like we've got a crest and a crest overlapping. So what type of interference is that?
Constructive.
Yeah, that's going to be constructive. Anywhere where we've got crest and crest overlapping is going to be constructive interference. But also any place where we have trough and trough overlapping would also count as constructive. So if we have a blank spot in between overlapping another blank spot in between, this, for instance, is going to be constructive. And so is this and this, the center of each of these sort of rectangle patches. And we end up with these sort of bands of constructive interference. Like this entire line is going to be constructive. This curve is going to be constructive. This curve is going to be constructive. So we get these constructive zones. And then in between, we're going to have destructive zones. So we get this alternating pattern of constructive, destructive, constructive, destructive. When those actually hit the wall, because you can't see light that's just passing through empty space. You can only see light that has bounced off of something to get to your eyes. So when this hits the wall, what we're actually going to observe is this alternating pattern of bright, dark, bright, dark, bright, dark, and so on. So the actual result of this is this pattern of bright and dark. Any questions on that so far?
Yeah, how can we tell if it's destructively interfering from this picture?
Destructive would be if you've got a crest and a trough overlapping. So let me draw an up close, a more up close picture of that. Let me clear out some of this. So the constructive would be if you've got a crest and a crest. So that would be the wave fronts that are drawn in. Or alternatively, a trough and a trough, because the in-between zone is supposed to be a trough. If you got a trough from one wave and a trough from the other wave, this spot right here, for instance, would be constructive as well. Destructive would be if you've got crest and trough overlapping. Let me draw this larger so we can see that in more detail. So let's say you've got a wave fronts coming in from one wave, and then also wave fronts from another wave. If you take a look at a crest from one wave, so let's say this crest, and then a trough from the other way, we'll just mark that as a dotted line. Should be halfway in between. If we take a look at this spot right here, for instance, that's a spot where the crest from one wave overlaps the trough from the other wave. And likewise right here, and also, for instance, this trough and this crest. So these spots would be destructive interference because those represent a crest from one wave and a trough from the other wave. And those are also going to form sort of a grid or line pattern as opposed to the constructive spots that we already talked about. Any questions on that? Of course, the problem with this wavefront diagram is that it quickly gets very cluttered. It becomes very difficult to see exactly what's going on. It's very useful for being able to visualize the big picture of what's happening. But if what we really care about is like at this point, is it going to be bright or dark? The wavefront diagram is not much use for that. So instead, what we typically do is use a ray tracing diagram. Instead of looking at what the individual crests and troughs are doing from each piece, instead we're going to be looking at the path that's taken by an individual beam of light. So for instance, you could have, let's say, a ray of light from this source, because you can treat the slits as sources, to any location you want. And we could also have a ray from the other slit to any location we want. But it's most interesting, most useful for interference to look at waves from both sources that both happen to be traveling towards the same destination. So let's take a look at that. Assuming we have wave from this slit to this location and from this slit to this location. That way we have two waves, one from here, traveling to the same place. And that's where we get the idea of interference. Any questions on that so far? So let's see how this plays into the idea of the total phase equation, total phase difference that we've been looking at for dealing with interference. The 2 pi t times difference in frequency minus 2 pi times difference in x over wavelength plus delta little phi, the phase shift, equals difference in total phase. First of all, is there anything that we know is the same about these two rays? What's not going to be different? What deltas are going to be 0?
The change in phase constant.
Yeah. We know that there's no difference in phase constant because where are these two waves coming from?
The same source.
Right. Same source. So there's no difference in phase constant. Yeah, time is also the same. There's no difference in time because both waves are arriving at the same time. So we don't even need a delta on time. But also, what do we know about the frequencies?
Has to be the same because it's the same source.
Right. These are coming from the same source. So there's no difference in frequency. And also, of course, they're the same wavelength. So wavelength can be factored out. We can take the entire time term that's being multiplied by no difference in frequency, so that's 0. There's no difference in phase shift because they're from the same source, unless there's something going on in between. Like maybe if you have something going on at one of the slits that flips the wave around, turning crest to trough and trough to crest, that could lead to a difference in phase shift. But assuming both slits just allow the light to pass through, there would be no difference in phase shift. And since wavelength is the same for both, we can factor that out of the delta. And so we just have 2 pi delta x divided by wavelength. So overall, we get, ignoring those zeros, we get 2 pi times the difference in path length divided by the wavelength equals difference in total phase. Also, it doesn't really matter whether delta phase is positive or negative. That's just going to be a matter of which order we subtract in. So I'm going to ignore the negative as well here. And let's say we specifically want constructive interference. In other words, a bright spot. Because constructive interference for light means we get a bright spot on the wall. So what has to be true in order to get constructive interference?
The total phase has to be what, like 2n pi?
Yeah, that total phase difference needs to be 2n pi. Because that gives you an even multiple of pi, in other words, a whole number of cycles. And a whole number of cycles offset means that the waves are really the same, or at least the crests and crests line up, trough and trough line up. So we want the waves to be offset by a whole number of complete cycles. If you fill that in, if you take this entire total phase and set it equal to 2 times n times pi, a whole number of cycles, we can actually solve that for delta x. How would you isolate delta x here?
So that would be lambda 2n pi divided by 2 pi. So that's lambda times n.
Yeah, the 2 pi's cancel out, and we just get lambda times n, or n times lambda. In other words, a whole number of wavelengths. If the difference between the short path and the long path is a whole number of wavelengths, that means they're offset by a whole number of cycles, so we get constructive interference. So this is really just the requirement to get constructive interference if the only difference between the two waves is they're traveling different distances. And note that that's not specific to just the double slit experiment specifically. What we've done so far works for any situation where the only difference is how far the waves travel. This leads to constructive interference in any situation where delta path length is the only difference. Any questions on that so far? Let me tidy this up a little bit then. So that's the main thing, that we want the total phase, or in order to get constructive interference, we need the difference in path length to be a whole number of wavelengths. That's true in general for any such situation where delta path length is the only difference. But let's see if we can apply that specifically to the double slit experiment. Let's see if we can explore what exactly is that difference in path length. And let's take a look at those paths. We have one path that is shorter and another path that is longer. But we need to know how much longer. Delta x is all about how much longer is the longer path. So if you sort of swivel this down, if you imagine just rotating this but keeping it the same length, if we just take this shorter path, let's call that x1, and swivel it down, x2 is x1 plus a little bit extra. That little bit extra is delta x. So this little bit of extra distance, that's the delta x that causes the interference. Let me draw that back in again. So just to label these, we've got x1, the top distance, and then x2 is the bottom distance, the distance from the lower slit to the point of interest. But we can write x2 as x1 plus a little bit extra. That little bit extra is the delta x we care about. So that's what we're actually trying to find. If we can figure out a way to algebraically express delta x in terms of everything else, then we can set that equal to n lambda to find any bright spots. Any questions on that so far? So let me introduce a little bit more notation here. Let's say we have, if we want to label this location, this point of interest here, we would label this location, we could label it with a distance. Like usually just to establish a coordinate system, we would trace across from the center of the slits to a point on the wall. We'd call that location y equals 0, and then we'd measure everything from there. So we would call, for instance, this distance we would call y. The height of the point of interest above this center point. By the way, what sort of interference would you expect at that center point? If we had rays of light going from this slit to the center and from this slit to the center. What do you notice about those two rays of light?
Constructive.
And how do we know for sure that's going to be constructive?
Because delta x is 0. All the terms in the phase difference equation is 0.
Yeah, we've already established that all the other ones are 0 because they're from the same source. But at this location specifically, because of symmetry, those rays are traveling exactly the same distance. Same distance because it's in the exact center means there's no delta x, and no difference at all automatically means constructive. There's no difference between the waves, so crest and crest line up, trough and trough line up, and so on. So the exact center is definitely going to be constructive interference. In fact, that's the point that we typically call the central maximum. So this is a bright spot called the central maximum. That's definitely constructive interference. Everything else we're going to be measuring from there. So we're going to be measuring y values as a height above or below that point. So anything above that point would be a positive y value, anything below would be a negative y value. And all the other locations, we could measure it as a distance, or we could also describe it as an angle, which often turns out to be more useful. For example, let's say we mark this location by drawing another line of sight from the center up to this point. What we're going to do is we're going to label that that location, that line of sight, as an angle. And we could call that angle, let's say, theta. So theta is the usual term we're going to use for that angle of elevation in all the equations we're going to be seeing. So we'll call that angle theta. The angle of elevation from the horizontal up to the point we care about. And we can actually use that angle to label the point. That way we don't have to worry about measuring distances. We can just say the angle of elevation is what we're using to label this point. Any questions on the terminology there so far? The only time, if the light is unchanged, if the light is just allowed to pass through without any alterations, then the center will always be a bright spot. If you have some other change, if you've got something messing around with the phase, like let's say one of the apertures has something that changes the phase of the light so that they're offset by, let's say, pi. If you do have a delta little phi of, let's say, half a cycle, then that changes the bright spot into a dark spot. But all that really does is reverse the pattern. So everything that was a bright spot becomes a dark spot, and everything that was a dark spot becomes a bright spot. But let's assume for the moment that this is unaltered, that there is nothing changing the phase. In order to get some more information about this, if we want to actually find delta x in terms of everything else, it helps to establish an extra triangle here. I'm going to put in one more line. Let's say a line from this slit to that border between delta x and the rest of the path. What should that angle be? Yeah, that should be a right angle, because we're assuming we rotate this straight down to the other one. So the shortest path to get there is going to be a right angle. Realistically, it's not going to be exactly a right angle, because these two, if we assume this is an isosceles triangle, x1, x1, and some other distance, these two angles have to be equal. But realistically, they're going to be something like 89.9 degrees and 89.9 degrees. So we can round it off to 90. If we draw out that triangle, I'm going to zoom in on that. Let's draw a bigger copy of that triangle. So we've got the distance between slits. We've got this delta x. And we've got this other arbitrary line making a right angle. So we know those together form a right angle. And we know some of the distances. We know this vertical distance is d, the distance between slits. And this short side here is delta x. That's the distance we actually want to find. Do we know any of the other angles? What angle does this diagonal make with the horizontal? Or what do we call that angle?
Theta?
Yeah, that's the theta angle, because that's the angle that the horizontal makes with the line of sight to the point of interest. So that angle is going to be theta. And we can get some other angles out of that as well. Because if this angle is theta, what would this angle have to be?
-90 minus theta.
Right, it's got to be 90 minus theta. Which actually tells us the other angle as well. If this is 90 minus theta, what does this one at the top have to be? That's got to be theta again, yeah. And this all has to do with the angle sum of the triangle. We know that the three angles in a triangle have to add up to 180. One of them is a right angle, so we've already used up 90. That means there's 90 left for the other two. So we've got 90 minus theta plus something equals 90. The something missing is an extra theta. So that means the angle at the top of this triangle is the same as the angle of elevation of the point of interest. And we can use that. We can use this theta as a reference point. So let's try some more trigonometry here. If we know this angle is theta, let's say that's some angle we can measure with a protractor. We can just measure the angle of elevation to the point of interest. Based on theta, what trigonometric function would relate delta x and d? Yeah, sine theta is going to be opposite over hypotenuse, so that's delta x over d. Solve that for delta x, and what do you get? How would you isolate delta x here?
D sine theta.
Yeah, multiply both sides by d. You get d sine theta. So that's the extra path length. If you've got a known angle of elevation and a known distance between slits times sine of the angle of elevation tells you the extra distance traveled by the longer path length. So that's the expression we get for delta x based on this situation from the geometry involved. But we also know from our analysis of interference that delta x has to be a whole number of wavelengths in order to get constructive interference. What can we do with those different delta x formulas? If you've got two different formulas for delta x, what can you do with those? Yeah, set them equal to each other. So to get constructive interference, we need d times sine theta to equal a whole number of wavelengths. As long as the distance between slits times the sine of the angle of elevation equals any whole number times the wavelength, that will guarantee constructive interference. So that's where you can find bright spots on this wall. And note that there's 4 unknowns here, or 4 values, I should say, 4 variables. So if you know any 3 of them, you can immediately find the 4th one. For instance, let's say you know the distance between slits, and you know that there's a bright spot at a certain angle. And also n basically represents which bright spot we're talking about. The central maximum would be n equals 0, because that's where we measure everything from. All the other bright spots would be like the first bright spot beyond the central maximum would be n equals 1. The next one would be n equals 2, then n equals 3, and so on. So n could be thought of as counting which bright spot you're talking about. N equals 0, n equals 1, n equals 2, etc. So if you can count which bright spot you're talking about from the center, then you can tell the value of n. And let's say you also know the distance between the slits. And you can measure the angle with a protractor. Then what's the only unknown left? Yeah, the wavelength. So you can solve algebraically for wavelength, and that tells you the wavelength of the light you're talking about. And this can allow you to find the wavelength with a very great degree of precision. If you can measure the angle very accurately, and of course n is going to be a whole number, so that's known precisely. And if you also know the distance between slits to a large degree of accuracy, then you can find the wavelength very accurately as well. Or alternatively, maybe you know the wavelength of light. Maybe you've got a laser that specifically emits a 500 nanometer beam of light. Then you can look for the bright spots, count up which bright spot you're looking at, measure the angle with a protractor, and then you can calculate the unknown distance between slits. And this actually turns out to be a remarkably useful way to measure distance between holes that are very close together. If you've got like a sheet of metal with 2 tiny pinpricks in it that are so close together that you can't even measure it with a ruler because it's smaller than the smallest gradation on your ruler, then this turns out to be a very useful way of accurately measuring that distance. You shine light on it with a wavelength you know, it gets through those 2 slits, and you can measure where the bright spots appear. Then solve for D, and that tells you how far apart those slits are going to be. Any other questions on that?
I had a quick question.
Mm-hmm.
Can you please re-explain of how you knew that theta was below the delta x?
This one here?
Like you knew that, yeah, like you knew that was theta from like the original drawing that you did.
Yeah, because we're defining theta as the angle of elevation from horizontal up to the line of sight to the point of interest. If we move the horizontal a little bit down to here and move this ray down to here, note that it doesn't quite match up. Like theta would be this angle.
Mm-hmm.
The actual ray of light is a little bit higher up, a little bit beyond that. But if we're assuming, again, that the distance between slits is very small and the distance to the other wall is very large, those rays are almost the same ray. Even though they're not exactly the same, they round off to the same angle as long as the distance between slits is small compared to the distance to the other wall.
Oh, okay. That makes a lot more sense. Thank you.
Mm-hmm. So realistically, it's not exactly theta, but it's close enough that we can round it off to theta. And then these 2 angles form a right angle, so this one has to be 90 minus theta. Any other questions on that? Also, what if you wanted a dark spot instead? If you were looking for a spot where no light appeared, what would you do differently? Going back to our total phase difference, how would you get destructive? Instead of being offset by a whole number of wavelengths, what would you want to have instead?
Half a wavelength.
Yeah, half a wavelength, or 1.5, or 2.5, or 3.5, anything that's something and a half wavelengths. So for destructive, we can take the exact same equation, but replace n with n plus 1/2. So destructive, exact same equation, but replace n with n plus 1/2. That way, that forces destructive interference instead of constructive interference. So you could use that to find the dark spots between the bright spots, but they should be pretty close to halfway between. Any other questions? All right, then I will see you next time.